So sampling distributions, just this whole idea is very large for the second semester. First thing we're going to talk about is something I've been kind of prepping you on for a while as a parameter. Now, for reasons that are no longer understandable to me, for whatever reason, I did not understand the difference between a parameter and a statistic when I was taking this class. And then when I taught it and I looked at the book maybe a little bit better, I went, well, that's simple. Does anybody remember what I said about a parameter last semester? No, it's okay. That was a long time ago, right? A parameter is a number that describes a population. Leading up to this chapter, whether something was a parameter or a statistic was a little less important, but now it's going to become more important. So a couple of the things that we've been using that are parameters are mu and sigma, right? Mu being the average of a population, or the mean of a population, and sigma being the standard deviation of a population. Usually, these are not things we can discover. They're unknowable unless they're given. Usually, parameters are given, okay? Unless your sample is, or it would be a census, unless you're able to take a census on a population that's small enough that you can actually know these. But like the U.S. population, nah, can't really do that, not reasonably. So then we have statistic. A statistic is a number that can be computed from a sample. Examples of statistics. Again, stuff we haven't used in a little while, but we're going to be using them again. S, or S sub x. Remember, that's your standard deviation of a sample. X bar, that's your mean of a sample. Y hat, that's the predicted output. N. And there are other parameters, of course, too. Those are just a couple of the bigger ones. We'll learn some more about those. So two very big ideas. Make sure you know the difference between a parameter and a statistic. All right, another huge idea, a sampling distribution. A sampling distribution of a statistic is the distribution of the values taken by the statistic in all possible samples of the same size from the same population. This one is another biggie. This one is a little tricky to wrap your head around. Give you guys a second to catch up on that. So how this works is this. Let's say this classroom is the population, okay? You guys are the population. Technically you are. You're the population of this class, right? And let's say I want to find out the average age. But I'm only going to take a sample of you, okay? Because you're way too big a population for me to sample everybody, right? Not in real life, but of course, we're imagining that this is a much bigger population. So let's say I take 3 of you at a time and I say, okay, what's your age, what's your age, what's your age? And I look at maybe years and months. And I take the average of those 3. And then I take another 3. And I find the average age. And I take another 3 and another 3 and another 3 and another 3. And I take all possible groups of 3. So for instance, Tom's age would be averaged with every one of your ages at one point if I took every possible group of 3. Does that make sense? And then I take all those values, and I put them into a table, into a distribution. Okay? What is that going to look like? Well, let's say I have something like 15, 16, 17, 18, and perhaps there's some 19-year-old, or And if I'm taking averages of 3, my guess is I'm going to get a bunch here. Right? Maybe quite a few in here. And I take all these averages and I put them on a graph in some way, like the counts, I guess. What would we expect for that sampling distribution to look like? Well, probably it's going to follow the normal curve, right? The idea of a sampling distribution is to understand that that's many, many samples. In fact, it's more than many, many. It's all possible samples. Now, is it possible to get all possible samples? Not only are we talking about a population that's probably unknowable, the actual mean, but we're talking about sampling all possible samples in a population. Does that seem possible? Yeah, it's not really possible, but that doesn't mean that we can't look at it and utilize it. So as long as we understand what they're talking about when they say sampling distribution, we're in good shape. So sometimes we'll get things that kind of look like sort of what I drew over there. And in that we'll have our normal-ish curve, approximately normal, right? Other times we'll get shapes that look like this. Perhaps. An important idea, sample size controls variation. larger the sample size, the lower the variation. The numbers are going to fit closer into the middle. So this is going to be an example of an increased sample size. And this gives us decreased variation. So this would be a small sample size taken many, many times versus a larger sample size taken fewer times because, well, I don't know, would there be less? Anyway, still many, many times. But your averages are going to be closer to the norm. So your sample size controls variation. What's variation? What's the difference between these guys? Let's say it's the same question. What's the average age? What's the difference between these two graphs visually? Yeah, it's more spread out. That's exactly right. That's variation. Variation is spread. There's lots of words for spread. Range, standard deviation is a form of spread. Variation. Yeah. So as you increase your sample size, you decrease the likelihood that you're going to get very different answers, like large swings in age, for example, if we're taking average ages. So, all right. Everybody so far so good? Okay. Unbiased statistic. What's a statistic? A number we can calculate from a sample, right? Unbiased estimator. A statistic used to estimate a parameter. Is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. Then the statistic is an unbiased estimator of the parameter. sketch up and I'll try to put some meaning to that. Let's pick a statistic to talk about. Let's say mean, okay? So mean is the average from a sample, right? That's a statistic, something we calculate from a sample. The thing that would be comparable to that as a parameter would be mu. It's the average of a population. So let's talk about mu and x bar. So a statistic, x bar, let's say, is used to estimate a parameter, mu. It is unbiased if the mean of its sampling distribution. Now we're talking about mean, but this is different. If the sampling distribution, if the sample is taken many, many times and the means, so we've got the mean of the sampling distribution, okay, is equal to the true value of the parameter. So this is saying that if we take many, many samples and find the average of many, many samples, and we graph that, and the mean of the average of many, many samples is the same as the mean of the average of the population, or the mu of the population, then they say that the statistic is an unbiased estimator. That they're the same, that's reliable. Okay, it's a way of saying that the statistic is reliable. Keep in mind, oftentimes, I mean, we're talking about sort of theoretical ideas here. Can I take every possible sample of a population? No. Can I find the information about a population? Probably not, right? So they're both sort of questionable, but we'll see how this ties together as we go along. Variability of a statistic how far away it is from the true mean is sort of a way of thinking of this. Variability of a statistic is described by the spread of the sampling distribution. So again, sampling distribution is that idea of taking a sample over and over and over again and taking all possible samples of a population. Variability is controlled by sample size, not population size. I have a note here too that problem 9.9 in homework deals with this. We'll have to keep an eye out for that. And we ran across a problem a while ago. Now I can't remember if it was a problem from the textbook or a test. I think it was a test question where they were talking about taking a sample from the Canadian population versus a sample from the United States population. And I think both sample sizes, if I remember the problem, were like 1,000 each. And the question was sort of along the lines of, you know, what can you expect from that? And I'm pretty sure it was a test question. So if your sample size is large enough, it doesn't matter how big the population is. It's your sample size that counts for trying to reduce this variability. Okay? And population needs to be at least 10 times larger than the sample. Needs to be at least 10 times larger than the sample. It could be 1,000,000 times larger than the sample, that's okay, but it needs to be at least 10 times larger. So in my beginning example where I said I'm going to take 3 of you and find the average age of 3 of you, the population in this class would be right at about 10 times larger than that, especially if everybody was here today, right? So I couldn't take 4 of you at a time and have those numbers work out right, or 10 of you at a time, given the size of this class. So 3 would be about as many as I could take at a time for a sampling distribution. Otherwise, my variability will become a problem. Okay. All right. Here's kind of an interesting way of thinking of variability. Bias versus variability. This is the last page before we move on to doing a couple problems, and then we'll get you guys some time to work. Let's say I have a target. And I'm throwing darts. And I throw the darts at the target, and they land something like this. Pretty good grouping. Got a good grouping there, but I'm not on target. This would be an example of high bias not on target. Oops. Target. But low variability. It's got a good grouping. Where does the good grouping come from? Sample size. The good grouping comes from sample size. If your sample size is big enough, your grouping should be good. You're reducing your variability. Where does the bias come from? Well, we just did some questions on bias, right? So your bias can come from the way something's questioned, who's asking the question, things like that, right? So we should know a little bit about bias. Variability, that's kind of the new thing. All right, so let's say I have another target, and I take aim with my question or my darts, and it looks like this. So how's my bias? Was I on target? It's high bias again. This is high bias. I'm off target still. I'm not hitting the target with my darts or my question. What do I want to know from the question? I'm not hitting it. So I must have had some bias in my question perhaps. What about variability? How's my grouping? It's pretty bad, huh? Pretty bad aim here. Maybe I'm throwing with not leading with the right foot. I'm doing something like this, right? It's not good. Okay, so this is high variability. Not only am I off target, but my answers are all over the place. This is poor grouping. Okay. Let me back up a little bit. Now that we've kind of looked at it this way, let's take a look at what these might look like under a normal curve. Okay. This high bias, low variability would look possibly like this. Very tall, normal curve, where my high point is my x bar, but the true mean of the population, that's the center of the target. I missed it. Maybe the true mean is way over here, right? Or it could be on the lower side, it doesn't matter. But it's my grouping is good. A nice tall normal curve, but I didn't hit what I was trying to hit. I didn't learn what I wanted to learn about the population. Does that make sense? So this one would look a little bit different. This guy, high variability, very low normal curve. I've got data way out here. Here's my x bar. It's the middle of the curve, but I didn't hit the bullseye even once. The bullseye being your mu. Okay, you're trying to learn about mu or your parameter, whatever. It could be sigma if you're looking at that parameter, but this is your parameter. Let's take it as mu. So my mu is somewhere away from x bar. It's not in the middle. It's somewhere else. I've missed it. I'm trying to learn about this, and I missed it. Okay? Make sense? All right. A couple more things here. What if I have a target that looks like this? I'm going to draw them a little smaller now because I'm running out of space on my page. What if I do this? Here's my target. I've hit the target. I even hit the center, and I'm close to the center. How's my bias? Yeah, low bias. We're centered around the middle, but my grouping's still pretty wide, isn't it? So this would be a low bias. We're on target. But we have high variability. Poor grouping. So this would be an example where my question was good, perhaps, if I'm asking. But maybe I didn't ask enough people. So I've got this. In this case, my curve would be very low. And my x-bar and my mu might be pretty close to one another. But I've got this variability issue where maybe it's normal, but it's really low. So how do I fix that? Here's how you fix that. The next example. The last example. I've asked my question. And I've got something that looks like this. And maybe I still have an oddball out there somewhere, but not so much so. So this would be a low bias. We're on target. And low variability. Good grouping. We might have an outlier. That's just the reality of statistics. But this would be a situation where our curve is nice and tall, and our x-bar and our mu are pretty much the same thing. Okay? And this is what we're looking for.